C. The language that built modern computing. Agenda. Structured programming. C. History. Why C? Compilation lifecycle. Getting started. Basic workflow. Building and running. Structured programming. Structured programming organizes code into clear blocks, loops, and functions instead of jumping around with unpredictable goals. Go-tos. If a program's logic breaks, well-structured functions make it far easier to isolate exactly where the failure happened. Almost every operating system, embedded device, and low-level library still traces its structure back to ideas C helped popularize. Any team writing code close to the hardware needs a language that maps predictably onto how the machine actually works. Writing large programs as a tangle of germs and labels doesn't scale. High languages doesn't scale. Procedural and object-oriented programming. Procedural programming organizes a program as a sequence of function calls operating on data passed between them. Object-oriented programming bundles data and behavior together into objects, adding another layer of structure on top. Procedural, object-oriented. Procedural, C, Pascal, functions operate on data. Object-oriented, C++, Java, objects bundle data plus behavior. Problems without structured programming. Single point of failure. An unstructured jump can send control anywhere, making bugs hard to trace. Code organized around gotos and labels is difficult to read, test, and hand off to another engineer. Hard to reuse logic without copying it, since there's no clean way to package a routine. Every programmer ends up inventing their own ad hoc conventions for organizing large programs. Difficult to reason about a function's behavior without tracing every possible jump into it. Misses out on portable, reusable functions that work the same across many machines. The C programming system. Source code is written in .c and .h files and kept in a source or Git repository. A compiler translates that source directly into native machine code for the target processor. The programmer manages all memory explicitly with functions like malloc and free. There's no runtime managing it for you. Other similar procedural languages: Pascal, Fortran, Go, partially. The advantages: compiles to extremely efficient native code with almost no runtime overhead. Gives complete explicit control over memory and hardware resources. Runs on virtually every processor and operating system ever built. A small, simple core language that's quick to learn and easy to reason about. Directly underpins most operating systems kernels, including Linux and Windows. Decades of stable, portable standard library functions relied on by nearly everything. Everything is a pointer, almost. One huge benefit is that in C, almost every data structure can be built and manipulated using pointers. Arrays, strings, and dynamic memory are all really just pointers with a bit of convention layered on top. Passing a pointer lets a function modify data in the caller without copying large structures around. Manual memory management means you decide exactly when memory is allocated and freed. This directness gives total control but also full responsibility for avoiding memory bugs. Structs and functions group related fields together into a single custom data type. Functions package logic behind the name that operates on data passed to it. Main.c every C program starts execution from a single main function. Manual memory management. Here, memory is allocated by hand with malloc and must be freed explicitly when done. History. Created by Dennis Ritchie at Bell Labs between 1969 and 1973. Evolving out of an earlier language called V, used to rewrite the Unix operating system, proving a system's language could also be portable across hardware. The book, The C Programming Language by Kernighan and Ritchie, published in 1978, defined the language for a generation. First standardized as ANSI C in 1989, followed by C99, C11, C17, and C23. As the standard continued to evolve, remains the foundation of most operating system kernels and a huge share of embedded software today. YC performance compiles to lean, fast native code with minimal overhead. Portability. The same source runs on nearly any processor with a C compiler. Simplicity. A small core language with few hidden behaviors to learn. Foundational. Still at the heart of operating systems, compilers, and embedded systems. Direct control. Explicit memory management with nothing hidden from the programmer. Enduring. Over 50 years old and still one of the most widely used languages in the world. The makefile. A makefile declares how source files are compiled and linked into a final program. Rules describe which files depend on which, so only what changed gets rebuilt. Running make simply reads this file and executes the necessary compiler commands. Never hand type long compiler commands repeatedly. Let the makefile remember them for you. C compilation lifecycle. Hash include expands, preprocess, gcc-s compile, gcc-c assemble, gcc objects link. Source is preprocessed to expand, includes and macros. Compiled to assembly, assembled into object code, and linked into a final executable. Getting started with C. This leads us to the three steps that turn source into a running program. GCC C translates a .c file into an object file. GCC combines object files into a single executable. Dot slash a dot out execute the compiled program. Basic workflow: compiling, linking, and running. Some call compile, link and run C's everyday loop. Fast. A C compiler can turn even a large codebase into a binary in seconds. Make and similar build tools recompile only the files that actually changed. Debuggers like GDB step through the compiled program line by line. Sanitizers and static analyzers catch memory bugs before they reach production. Supports many workflows, operating systems, embedded firmware, compiler, device drivers. Works the same, source for source, on nearly every platform with a C compiler. Any questions? Thank you.